So in my last video, I had claimed that we had solved flags 3 and 4, and that's a half lie. We had technically solved flag 3, just discovered the base of flag 4, but we hadn't gone any further with it, and I wanted to put it in its own video because this is going to be kind of time consuming. There's a method of doing this that involves putting a breakpoint through GDB, which is the GNU debugger, and then jumping to the function or the method that we want to call. And that's all fine and well, and I'll show you how to do that towards the end of this, sure. But I wanted to explain stack smashing. So after doing a little research myself, so a stack buffer overflow occurs when a program writes to a memory address on the program's call stack, and that call stack is just a data structure that stores information about the active subroutines of the program, and you can bleed information out of these different memory addresses essentially by manipulating them, filling them full of characters and things that aren't supposed to be there, right? And this usually results in crashes, are these things known as segmentation faults. So while the program writes data to a buffer, we can force it to overrun the buffer's boundary, like I was just saying. So picture there's a pool, you fill that pool up, and it's going to do what? It's going to overflow. It's kind of like you have a cup of water, only so much water can fit in the cup, keep filling it up, it just spills out. So a buffer, this is a good thing to know here, is just the region of physical memory storage used to temporarily store data in the program while it's being moved from one location to another. And that opens up a lot of possibilities. So overfilling a buffer on the stack usually misguides program execution, like I was saying. So if talisman, this bin object that we've gotten, allows us to mess with it and essentially put data into it, pull data out of it, we could potentially reveal data, functions, etc. that weren't accessible. So let's start with just file talisman like I've ran here. We can run it again if we want to be clever, I don't know. It says that it's an ELF 32-bit LSB executable. So executable in linkable format is ELF, and LSB stands for Linux Standard Base, and it's 32-bit. That's the most important part besides the acronyms. The acronyms be damned. It's 32-bit, and this will give you nothing but problems unless you execute these commands here, which I've already done. But these commands here pretty much give us the architecture to mess with 32-bit platform, or excuse me, executables on our 64-bit platform. So without this, you will not be able to run Talisman. You'll do, you'll chmod, do your thing, and go to do Talisman like that, and it'll just say file not valid, file not found, not an accurate directory. I mean, I can go on and on. You have to have this 32-bit architecture to get anywhere with this. So run this command right here, which like I said, I've already done. And then run an update, app-get update. And then last but not least, here come the good stuff. We'll get these guys in there. Which, like I said, I already have, but still, crucial. Have to do it to solve it. Have to. Unless you're on a 32-bit system. But I'm just, again, remember in my first video I said I'm an asshole who's good at making assumptions? I'm going to assume that everybody in modern day is on freaking 64-bit, okay? So using object dump, which is a command line tool, we can use tacd, which is a disassemble option, on our talisman, and this spits out functions that are supposedly contain information. So right here, disassemble sections. That's why I take notes, because I can read it more eloquently than I can say it on the fly. It disassembles only the sections of the program or the binary file which are expected to contain instructions. So you can start looking through here, and we'll just start from the bottom up because the good stuff should be here towards the bottom further, honestly. And you're going to expect to see like a main, for example. And then I see chant to break spell right here. And keep that in mind. Keep this number right here in mind. Its address. Let's see if there's anything else here. Where talisman, my printf, hide, unhide, and then just nonsense. So let's see. So we have our function information, and this is on a Little Indian system. I don't want to get too far into Little Indian, but it's the least significant byte, so the lowest address is stored first. So if you were to feed information as byte 3210, it would be stored in memory in little Indian format, the exact opposite order that you input it in. So if you go byte 3210, it's literally going to come out 0123. That's how it's going to be stored in little Indian. And there are cleaner ways of displaying the functions of our talisman, but this object dump, it's just kind of nice to know, especially if you're into programming and whatnot, or if you do low level stuff. It's kind of just one of those things. It's like that EXIF tool I told you to keep in mind. While you might not necessarily just need to use that right now, it's just the way I'm going about it. Keep it in mind for the future because it serves a purpose in a big way. So to get the same effect without all the googly gop here that we're seeing, if you're not interested in any of this or don't care on this level, you just do GNU debugger, which is apt-get install GDB if you don't have it already. But GDB and then just do talisman. And then you can go info functions, and we get all our function names and their address there without, in a very clear format. Let's just say it that way. So let's see. I see our wear talisman like we had already discovered, and chant to break spell. So chant to break spell and wearing the talisman, those sound interesting to me. And notice that our address for the active function call on the chant to break spell is this guy right here. Now that's what we want to access. We want to get chant to break. All right. So when we do GDB talisman and we do run and we were looking at our functions and like the flow and how we wanted to get into chant to break spells, when we run it, it executes main. When it executes main, we're presented with this right here. You found the talisman. Do you want to wear it? Now, upon entering your response to do you want to wear it, whether it's yes, no, or Mary, glory, hallelujah, when it says nothing happens, it is calling the wear talisman function. So how do we get in? So it's going to be Python tag C, and then we're telling it do this command, print, then we're going to say character A, and we want to do that times 32, so print 32 A characters. And then this is the part I don't want to botch. The actual address reverse. So now we want to say print 32 A characters into X37 X8A. God, you think I'd be faster at this with as much programming as I've actually done, which I guess in the grand scheme of things isn't that much, but it still feels like enough to be quick without the 10 key, and I'm just not, so forgive me people who are. Alright, and then we're going to pipe that into our talisman actually being ran. And looky there. So after pumping 32 A characters into that address, little Indian style, we have found that it ran, so it called main, it ran the program, and then right after main, it's supposed to call where talisman, which it did, and then it skipped without any user input right into that memory address where this is stored, and it has been bled now. You can see that there's a segmentation fault, so it's broken. You know, we're outside of our bounds here, but this is what was contained within that function, and this is Flag4. And if you want to see the quick and dirty way, so you don't have to know anything about Python, you don't have to know anything about Little Indian, you don't have to know anything about architecture, you don't have to know anything about any of this object dump, assembly, any of that crap. Easy way to do it is just go GDB talisman, and then you can do, what is it, B main, I believe. You set your breakpoint at your main, and then you do, and does it run? No, maybe it's jump and then the name of the function we want to jump to out of our breakpoint. What is it? Chant to break. There we go. So yeah, if you set that break, that's literally the easy way to do it. Break it main, set your breakpoint, and then jump from your breakpoint into the actual just function itself. You literally just declare where you want to go, and you can jump right to it because you're broken at main, you're paused at main. So it's not, execution isn't just automatically happening. You're kind of like, pause right here. Let me make a choice. I'll tell you manually where I want you to go. And you see how it says right here, after we jump to chant to break spell, it says continuing at right here. Okay, so keep that in mind, because chant to break spell is not actually located, like that's not actually the address of chant to break spell. This is an address within chant to break spell after being called, and hopefully I still have it up here. See, chant to break spell's got A37 on as the last three. This is A3B, so this is happening within that, and this is how you can tell that this is the contents of that function being called. So long story short, we have Flag4, and we have chant these words at U31337. Well, the last time we had to chant, and it had a U and it had a number, that was UDP port. So I'm assuming that we have to now chant this flag, decode this flag, and chant it at port UDP 31337. So let's go ahead and just append this to our notes here so that we don't lose track of it. And I will see you guys in the next video as we continue to work on flags 5 and 6. Thanks for watching.